Okay, hi everyone, welcome back to this video series on Windows Server 2012, working with classless inter-domain routing. Microsoft uses an alternate way to write address ranges called classless inter-domain routing, CIDR, pronounced CIDR. CIDR is a shorthand version of the subnet mask. For example, an address of 131.107.2.0 with a subnet mask of 255.255.255.0 is listed in CIDR as 131.107.2.0/24 because the subnet mask contains 24 ones. An address listed as 141.10.32.0/19 would have a subnet mask of 255.255.224.0 or 19 ones. The default subnet mask for class B plus 3 bits. Figure 8.12 subnet mask represented by ones. Subnet mask in binary 1111 11111111111111111100000000. Subnet in decimal 255.255.255.0. Spaces in the above example are only for illustrative purposes. The subnet mask in decimal would actually appear as 255.255.255.0. Let's say an internet company has assigned you the following Class C address and CIDR number 192.168.10.0/24. This represents the Class C address of 192.168.10.0 and a subnet mask of 255.255.255.0. Again, CIDR represents the number of ones in a subnet mask. For example, a CIDR number of /16 stands for 255.255.0.0. 111.111.111.00000000000. The following is a full list of all CIDR numbers, starting with a Class A default subnet mask and their corresponding subnet masks. CIDR mask, CIDR mask, CIDR mask, /8 255.0.0/17, 255.255.128.0/25, 255.255.255.128, /29 255.128.0.0, /18 255.255.192.0/26 255.255.255.192 /10 255.192.0.0/19 255.255.224.0/27 255.255.255.224 /11 255.224.0.0/20 255.255.240.0 /28 255.255.255.240 /12 255.240.0.0/21 255.255.248.0/29 255.255.255.248 /13 255.248.0.0/22 255.255.252.0/30 255.255.255.252/14, 255.252.0.0/23, 255.255.255.254.0/31, 255.255.255.254/15, 255.254.0.0/24, 255.255.255.0/32, 255.255.255.255/16, 255.255.0.0. Quickly identifying subnet characteristics using CIDR. Given the limited time, you have to dispatch questions in the structured environment of a Microsoft certification exam. Every shortcut to coming up with the correct answer is a plus. The following method using CIDR notation can shave minutes off the time it takes you to complete a single question. Since you already understand the underlying binary technology at the heart of subnetting, you can use the following shortcuts, one for each address class, to come up with the correct answer without working in binary. Identifying class C subnet characteristics. Consider the host address 192.168.10.504/27. The following steps flesh out the details of the subnet of which this address is a member. 1. Obtain the CIDR notation prefix length for the address by converting the dotted decimal mask to CIDR notation. In this case, /27 corresponds to a mask of 255.255.255.244. Practice converting between these notations until it becomes second nature. 2. Using the closest multiple of 8 that is greater than or equal to the prefix length, compute the interesting octet, the octet that increases from one subnet to the next in increments other than 1 or 0. Divide this multiple by 8. The result is a number corresponding to the octet that is interesting. In this case, the next multiple of 8 greater than 27 is 32. Dividing 32 by 8 produces the number 4, pointing to the fourth octet as the interesting one. 3. To compute the incremental value in the interesting octet, subtract the prefix length from the next higher multiple of 8, which in this case is 32. The result, 32 minus 27 is 5. Raise 2 to the computed value, 25 equals 32. The result is the incremental value of the interesting octet. 4. Recall the value of the interesting octet from the original address, 50 in this case, starting with 0. Increment the incremental value until the value is exceeded. The values then are 0, 32, 64, and so on. 5. The subnet in question extends from the increment that is immediately less than or equal to the address's interesting octet value to the address immediately before the next increment. In this example, 192.168.10.50/27 belongs to the subnet 192.168.10.32, and this subnet extends to the address immediately preceding 192.168.10.64, which is broadcast address 192.168.10.63. Note that if the interesting octet is not the fourth octet, all octets after the interesting octet must be set to 0 for the subnet address. 6. The usable range of the addresses for the subnet in question extend from 1 higher than the subnet address to 1 less than the broadcast address, making the range for the subnet in question 192.168.10.33 through 192.168.10.62. As you can see, 192.168.10.50/27 definitely falls within the subnet 192.168.10.32/27, identifying class B characteristics. Using the steps in the previous section, find the subnet in which the address 172.1676.12 with a mask of 255.255.240.0 belongs. 1. The corresponding CIDR notation prefix length is 4/20. The next multiple of 8 that is greater than 20 is 24. 24x 8 equals 3. Octet 3 is interesting. 24 minus 20 equals 4. So the incremental value is 24 equals 16. 4. The increments in the third octets are 0, 16, 32, 48, 64, 80, and so on. 5. The increments of 64 and 80 bracket. The address's third octet value of 76, making the subnet in question 172.16.64.0. After setting all the octets after the interesting octet to 0, this subnet's broadcast address is 172.16.79.255, which comes right before the next subnet address of 172.16.80.86. The usable address range that it then extends from 172.16.64.1 through 172.16.79.254, identifying Class A subnet characteristics. Try it one more time with 10.16.127.255/14. Combine some of the related steps if possible. 1. The prefix length is 14. The next multiple of 8 that is greater than or equal to 14 is 16. 16 multiplied by 8 equal 2. So the second octet is interesting. 2, 16 minus 14 equals 2. So the incremental value in the second octet is 2 equals 4. 3. The corresponding second octet value of 6 in the address value falls between 4 and 8 increments. This means that the subnet in question is 10.4.0.0, setting octets after the second one to 0, and its broadcast address is 10.7.255.255. 4. The usable address range from 10.4.0.1 through 10.7.255.254. Determining quantities of subnets and hosts. The general technique described in the previous section is also useful when trying to determine the total number of subnets and hosts produced by a given mask with respect to the default mask of a class of address in question. For example, consider the Class B address 172.16.0.0 with a subnet mask of 255.255.254.0. This is a prefix length of 32 bits. When you subtract the default prefix length for a Class B address of 16 from 23, you get the value 7. Raising 2 to the 7th power results in the value 128, which is the number of subnets you get when you subnet a Class B address with the 255.255.254.0 mask. Determining the number of hosts available in each of these 128 subnets is simple because you always subtract the prefix length that the subnet mask produces, 23 in this example, from the value 32, which represents a total number of bits in any IP address. The difference, 9, represents the remaining numbers of zeros or host bits in the subnet mask. Raising 2 to this value produces the total possible number of host IDs per subnet that this subnet mask allows. Remember to subtract 2 from this result to account for the subnet and broadcast address for each subnet. This gives you the actual number of usable host IDs per subnet. In this case, this value is 29 minus 2 equals 510. Repeated practice with this technique will reduce your time to obtain the desired answer to mere seconds, leaving time for more challenging tasks in each question. You have a wealth of examples and scenarios in this chapter, as well as in the review questions, on which to try your technique and build your trust in this faster method. Supernetting. Let's take a look at a different type of subnetting. Class B addresses give you 65 and 534 addresses, but let's say you have 1,000 users. Would you really need a Class B address? Not if you're supernetting. Supernetting allows you to have 2 or more blocks of contiguous super network addresses. So what does that actually mean? Class C addresses give you 254 usable addresses. So if you need 1,000 users, you could set up supernetting of 4 Class C addresses that are contiguous. Example, 192.168.16.0, 192.168.17.0, 192.168.18.0, 192.168.19.0. When you set up supernetting for a Class C, you would use a Class B subnet mask. When you set up supernetting for a Class B, you would use a Class A subnet mask. This allows you to use multiple classes to get larger number of hosts without taking up an entire class. So the subnet mask for the above example would be 255.255.252.0 or /22. The reason we use this subnet mask is because a 252 subnet mask allows for 4 subnets. Each of the above Class C numbers would equal 1 subnet on this network. Understanding IPv6. Internet Protocol version 6 IPv6 is the first major revamping of IP since RFC 791 was accepted in 1981. Yes, the operation of IP has improved, and there has been a few bells and whistles added, such as NAT, for example, but the basic structure is still being used as it was originally intended. IPv6 has actually been available to use in Microsoft operating systems since NT 4.0, but always had to be manually enabled. Windows Vista was the first Microsoft operating system to have it enabled by default. It is also enabled by default in Windows 7, Windows 8, Windows Server 2008, Windows Server 2008 R2, and Windows Server 2012 R2. And it probably will be in all Microsoft operating systems from this point on. TCP and UDP, as well as the IP applications such as HTTP, FTP, SNMP, and the rest are still being used in IPv4. So you might ask, why change to the newer version? What does IPv6 bring to your networking infrastructure? What is the structure of an IPv6 address? How is it implemented and used within Windows Server 2012? I'll answer all of those questions and more in the following sections. IPv6 history and need. In the late 1970s, as the IP specifications were being put together, the vision of the interconnected devices was limited compared to what we actually have today. To get an idea of the growth of the internet, take a look at Hobbes' internet timeline in RFC 2235 As you can see, in 1984, the number of hosts finally surpassed 1,000, 2 years after TCP and IP were introduced. With 32 bits of addressing available in IPv4, it handled 1,000 plus hosts just fine. And even with the number of hosts breaking the 10,000 mark in 1987 and then 100,000 in 1989, there were still plenty of IP addresses to go around. But when the number of hosts exceeded 2 million in 1992 and 3 million in 1994, concern in the industry started to build. So in 1994, a working group was formed to come up with a solution to quickly dwindling usable addresses availability in the IPv4 space. Internet Protocol Next Generation IPNG was started. Have you heard of IP address depletion being a problem today? Probably not as much. When the working group realized that it could not have IPv6 standardized before the available address might run out, they developed a standardized network address translation, NAT, as an interim solution. NAT, or more specifically, the implementation of NAT called Port Address Translation, PAT, took care of a big portion of the problem. NAT works very well, but it does have some limitations, including issues of peer-to-peer applications with IPv4 addresses embedded in the data, issues of end-to-end traceability, and issues of overlapping addresses when two networks merged, because all devices in an IPv6 network will have a unique address and no network address translation will take place. The global addressing concept of IPv4 will be brought back. The address put on by the source device will stay all the way to the destination. Thus, with the new and improved functionality of IPv6, the drawbacks of NAT and the limitations of IPv4 will be eliminated. New and improved IPv6 concepts. Several elements of IPv4 protocol could use some enhancements. Fortunately, IPv6 incorporates those enhancements as well as new features directly into the protocol specification to provide better and added functionality. The following list includes new concepts and new implementations of old concepts in IPv6, larger address space, 128-bit versus 32-bit, auto configuration of internet accessible addresses with or without DHCP. Without DHCP, it's called stateless auto configuration, more efficient IP header, fewer fields and no checksum. Fixed length IP header. The IPv4 header is variable length with extension headers beyond the standard fixed length to provide enhancements. Built-in IP mobility and security. Although available in IPv4, the IPv6 implementation is a much better implementation. Built-in transition schemes to allow integration of the IPv4 and IPv6 spaces. ARP broadcast messages replaced with multicast request. Here are some details about these new features. 128-bit address space. The new 128-bit address space will provide unique addresses for the foreseeable future, although I would like to say that we will never use up all of the addresses. History may prove me wrong. The number of unique addresses in the IPv6 space is 2128 or 3.4x 1038 address. How big is that number? It's enough for toasters and refrigerators to all have their own addresses. At this point of reference, the nearest black hole to Earth is 1600 light years away. If you were to stack 4 BB pellets from here to the nearest black hole and back, you would need 1 .51x1022 BBS. This means you could uniquely address each BB from Earth to the black hole and back, and still have quite a few addresses left over. Another way to look at it is that the IPv6 address space is big enough to provide more than 1 million addresses per square inch of the surface area of the Earth. Oceans included auto configuration and stateless auto configuration. Auto configuration is another added improved feature of IPv6. We've used DHCP for a while to assign addresses to client machines. You should even remember that IPA can be used to assign addresses automatically to Microsoft DHCP client machines in the absence of a DHCP server. The problem with IPA is that it confines communication between machines to a local LAN, no default gateway. What if a client machine could ask whether there was a router on the LAN, or what network was it on? If the client machine knew that, it could not only assign itself an address, it could also choose the appropriate network and default gateway. The stateless auto configuration functionality of IPv6 allows the clients to do this. Improved IPv6 header. The IPv6 header is more efficient than the IPv4 header because it is fixed length with extensions possible and has only a few fields. The IPv6 header consists of a total of 40 bytes. 32 bytes source and destination IPv6 addresses, 8 bytes version field, traffic class field, flow label field, payload length field, next header field, and hop limit field. You don't have to waste your time with a checksum validation anymore, and you don't have to include the length of the IP header. It's fixed in IPv6. The IP header is variable length in IPv4, so the length must be included as a field. IPv6 mobility. IPv6 is only a replacement of the OSI layer 3 component, so you'll continue to use the TCP and UDP components as they currently exist. IPv6 addresses a TCP issue, though specifically TCP is connection orientated, meaning that you establish an end-to-end communication path with sequencing and acknowledgements before you ever send any data, and then you have to acknowledge all of the pieces of data sent. You do this through a combination of an IP address, port number, and port type socket. If the source IP address changes, the TCP connection may be disrupted, but then how often does this happen? Well, it happens more and more often because more people are walking around with a wireless laptop or a wireless voice over IP VoIP telephone. IPv6 mobility establishes a TCP connection with a home address, and when changing networks, it continues to communicate with the original endpoint from a pair of address as it changes LAN, which sends all traffic back through the home address. The handing off of network addresses does not disrupt the TCP connection state. The original TCP port number and address remain intact. Improved security. Unlike IPv4, IPv6 has security built in. Internet Protocol Security IPsec is a component used today to authenticate and encrypt secure tunnels from a source to a destination. This can be from the client to the server or between gateways. IPv4 lets you do this by enhancing IP header functionality, basically adding a second IP header while encrypting everything behind it. IPv6, you add this as standard functionality by using extension headers. Extension headers are inserted into the packet only if they are needed. Each header has a next header field, which identifies the next piece of information. The extension headers are currently identified for IPv6 or hop by hop options, routing and fragment destination options, authentication and encapsulation security payload. The authentication header and the encapsulation security payload header are the IP-specific control headers. IPv4 to IPv6 interoperability. Several mechanisms in IPv6 make IPv4 to IPv6 transition easy. A simple geostack implementation where both IPv4 and IPv6 are installed and used is certainly an option in most situations so far. This doesn't work so well because most of us aren't connected to an IPv6 network and our internet connection is not IPv6, even if we're using IPv6 internally. Therefore, Microsoft includes other mechanisms that can be used in several different circumstances. Intra-site automatic tunnel addressing protocol, ISATAP, is an automatic tunneling mechanism used to connect an IPv6 network to an IPv4 address space not using NAT. ISATAP treats the IPv4 space as one big logical link connection space. 624 is a mechanism used to transition to IPv4. This method, like ISATAP, treats the IPv4 address space as a logical link with each IPv6 space in transition using a 624 router to create endpoints using the IPv4 space as a point-to-point connection, kind of like a WAN. 624 implementations still do not work well enough through a NAT, although a 624 implementation using an application layer gateway, ALG, is certainly doable. Teredo is a mechanism that allows users behind a NAT to access the IPv6 space by tunneling IPv6 packets in UDP. Pseudo interfaces are used in these mechanisms to create a usable interface for the operating system. Another interesting feature of IPv6 is that the addresses are assigned to interfaces or pseudo interfaces, not simply to the end node. Your Windows Server 2012 or 2 will have several unique IPv6 addresses assigned. New broadcast methods. IPv6 has moved away from using broadcast. The three types of packets used in IPv6 are unicast, multicast, and anycast. IPv6 clients then must use one of these types to get the MAC address of the next Ethernet hop default gateway. IPv6 makes use of multicasting for this, along with new functionality called neighbor discovery. Not only does ARP utilize new functionality, but ICMP, also a layer 3 protocol, has been redone and is now known as ICMP6. ICMP6 is used for messaging, packet too large, time exceeded, and so on, as it was in IPv4, but now it's also used for the messaging of IPv6 mobility. ICMP6 echo request and ICMP6 echo reply are still used for ping. So I'm going to leave it here today for this video. If you like this, then please consider like, sharing, and subscribing. Thank you.